this work. So thanks everyone for being here. It's really great to be back in Sydney. My talk today is about writing good tests, but first we should think about why do we write tests at all? Sure. The joystick, okay. Whoops, that seems okay. All right, we'll figure it out. So books about programming say that tests are about finding bugs in your program. So this book says, testing is a determined, systematic attempt to break a program that you think is working. And this is true. This is why programmers write tests. But for most of us here today, it's not why we write tests, because we are not mere programmers. We are software engineers. And let me tell you what I mean by that distinction. So do I just click it? There we go. Okay. I like to say that software engineering is what happens to programming when you add time and other programmers. And so programming means getting a program working. You have a problem to solve, you write some code, you test it, you debug it, you run it, you get your answer, and you're done. And that's already pretty difficult, and testing is a really important part of that process. But software engineering means doing all of that in programs that you keep working over a long period of time and with other people. And that changes the nature of your testing. So let's start by looking at tests for a binary search function. This function find takes a sorted slice and a target value and a comparison function, and it uses binary search to find and return two things. First, the index where the target would appear if it were present, and second, a Boolean saying whether it is actually at that location. And most of the time, binary search code is buggy, and this one is buggy, so let's test it. That worked. That's cool. Here's a nice interactive tester for a binary search function. You type two numbers, n and t, and it makes a slice of n elements containing multiples of 10, and then it does a search for t in the slice, and then it prints the answers, and then it repeats. And this may seem trivial or silly, but how many of you have ever tested production code just by running at and poking at it for a while and saying, okay, that's good? All of us have done that. And when you're programming, an interactive tester like this can be very useful for finding bugs. Although so far, the code does appear to be working. But this tester is only good for programming. If you're doing software engineering, meaning you're keeping the program running over a long time and working with other people, then this kind of tester is really not too useful. You need something that can be run by everyone else, every day, when they're working on this code or other code, and that can be run automatically by a computer on each commit. And the problem with testing your program by hand is that only makes sure that it works today. You want automated continuous testing to make sure that it keeps working tomorrow and into the future, even if other people who don't know the code as well start working on it. And to be clear, those other people who don't know the code as well might be you in 6 months or 6 years. So here's a software engineer's test. You can run it without any knowledge of what the code should do. Any colleague or any computer can run this using GoTest and know exactly right away whether the code passes. And so you've seen tests like this already, I'm sure. And the software engineering ideal is to have tests that catch every possible mistake that you could make later. And if your tests meet that ideal, then you should, in theory, be comfortable shipping your code to production automatically anytime all your tests are passing, which is what people call continuous deployment. And if you don't do this already, if the idea of it makes you nervous, then it's worth thinking about why. Either your tests are good enough or they're not. If they are good enough, then why not do it? And if they're not good enough, then that sort of nagging voice telling you that is probably also telling you which sections need better testing, and you can listen to that and use that to improve your testing. So a few years back, I was working on the server for the new Go website, go.dev, and we deployed the site manually back then, each time enough changes had accumulated. And at least once a week, I would make a change and test it, and it seemed to work locally, and I would deploy it, and the web server wouldn't be able to serve any pages. And that was kind of annoying. It was kind of embarrassing for me. And the solution here was better tests and then automated continuous deployment. So now every time a commit lands in the repo, we use a cloud build program to run the tests and then deploy to a fresh server and then run more tests that run in production. And then if they all pass, then we change the traffic to go to the new server. And this made things better 2 different ways. The first is that I stopped causing outages, which I feel good about. And the second is that everyone stopped having to think about how to deploy the web server at all. So it used to be that if someone submitted a typo fix to the website, then like someone else had to go and deploy it. And now you just do the usual send a change out, get it reviewed, get it submitted, and then 5 minutes later it's just on the site. So that's much better. Oh, too far. That's okay, we'll just stay on this slide. So what makes tests good? To be confident that your program won't break when other people edit it, and to be confident that your program can be pushed to production anytime the tests are passing, you need a really good set of tests. And in general, what makes tests good is the same thing that makes non-test code good. You need hard work and attention and time, and there's not silver bullets or hard rules for that. But I do have some tips that apply most of the time, or some of the time, depending on the tips. And so I'm going to go through 20 tips in this talk, and this is the first tip, which is make it easy to add new test cases. This is by far the most important tip, because if it's not easy to add new test cases, you won't do it. So here is a minimal useful Go test. This is the most trivial test of the function foo that's actually useful. And we designed Go tests to be very easy to write so that it is easy to add new test cases. There's no bookkeeping or ceremony here that gets in your way. And at the level of package testing, this is pretty good. But in a specific package, you can do even better. There we go. I'm sure you already know about table-driven tests. We encourage table-driven tests precisely because they make it so easy to add new test cases. So suppose we have only this one test case, and we think of a new case that we want to test. We don't have to write any new code at all. We just write one line of data. That's about as good as it gets for making tests easy to add. But it does raise the question of which tests should we add? So tip number 2, use test coverage to find untested code. After all, if the tests are not running the code, they can't find any bugs in it. And Go ships with built-in support for test coverage. And this is what it looks like. You can run go test minus cover profile to write a coverage profile, and then you run go tool cover to view it in your browser. And in the display, we can see that our single test case is actually not a very good one, because the actual binary search code is entirely red, meaning it's entirely untested. So the next step is to look at the untested code and think about what kinds of tests would cause those lines to run. On closer examination, we only tested with a single empty slice. So let's add a case with a slice that isn't empty. That seems worth testing. And we can run coverage again. And this time, instead of the web view, I'm running a little program I wrote called uncover. And uncover prints the lines of code that are not covered by the test. And so in this case, after we add this extra test case, uncover shows us there's just one line left that isn't executed by the tests. And it's the line that moves further into the array, or into the slice, which makes sense since in the test case we wrote, the target was the very first element. So we haven't tested moving into the slice. So let's add, whoops, that didn't work. Let's add one more test, searching for the last element. When we run the test, it passes, and we have 100% coverage. So that's great. So now are we done? Well, we're not. And that takes us to the next tip, which we've already seen, maybe. Oh, too far. Tip number 3 is that coverage is no substitute for thought. Coverage is very useful for pointing out parts of your code that you might have forgotten about, but mechanical tools are no substitute for actually thinking about what might be difficult about this problem that I'm solving. What are the subtle inputs that I really need to make sure I handle correctly? And so code with 100% testing coverage can absolutely still have bugs, and this code does. So what's missing here? One thing to notice is that the only test case that returns false, so it doesn't find the target, is the empty input. So probably we should check not finding the target in non-empty inputs. And in particular, we should look for a target being at the beginning of the slice, or all the way at the end of the slice, or somewhere in the middle. So let's add 3 more test cases. And notice how easy it is for us to add new test cases. Remember, it has to be easy. If it's too hard, you won't bother. You can also see how we're starting to enumerate all the possible ways that a binary search can go wrong. And these tests constrain all future development so that it continues to work in the future. Every piece of code that we have that we run against these tests will at least run this well. Now, when we run these tests, it turns out they fail, because while the returned index I is correct, the Boolean indicating whether the target is present is wrong. So if we look at that, reading the code, clearly the return statement is wrong. It was only checking that the index was in range, and we need to add the code in bold that checks that the value is actually equal to the target. So we make that change, we run the tests, and now they pass. So we feel pretty good now. Coverage is happy. We've thought hard about it. What more can we do? Tip number 4 is to write exhaustive tests. If you can test every possible input to a function, you absolutely should. And this may be unrealistic. Most functions take an infinite number of inputs. But you can usually test all inputs up to a certain size and under certain constraints. And when you can do that, you absolutely should. So here is an exhaustive test for binary search. We start, this is going to be hard. There we go. We start by making a slice of 10 elements, specifically the odd numbers, 1, 3, 5, up to 19. Whoops. Okay. Then we consider all possible length prefixes of that slice. That's good. Move on. There we go. And then for each prefix, we consider all possible targets from 0, which is the smaller than all the values in the slice, up to twice the length, which is larger than all the values in the slice. And this will exhaustively test every possible search path through every possible size slice into every possible location up to our length 10 limit. But now, how do we know what the answer is? We could do some math based on the specifics of the test cases, but there is a better, more general way, and that is to write a reference implementation. And usually the reference implementation is a simpler, slower version of the code that you have that isn't suitable for production, but is suitable for tests. So in our case, we have this function slowFind. We get the correct answers from slowFind, then we check that they agree. And since the inputs are small, using a linear search is totally fine. And this pattern of generating all possible size inputs up to some size and comparing against a reference is very powerful. One important thing it does is cover all the small cases that are corner cases. So a 0-element slice, 1-element slices, slices with odd lengths, slices with power of 2 lengths, and so on. Because the vast majority of bugs in most programs can be reproduced by small cases. So if you can just generate all the small cases up to a certain size, testing all of them is very effective. So it turns out that this test passes. So our thinking was actually pretty good so far. Whoops. But if the exhaustive test fails, then that means that find and slowFind disagree. So at least one of them is buggy, but we don't know which one. So it helps to have a direct test of slowFind. And that's easy since we already have a table of test data. And so this is another benefit of table-driven tests. The tables can be used to test more than one implementation. What's going on here? Tip number 5, separate test cases from test logic. In a table-driven test, the cases are all in the table, and the loop that processes them is the test logic. And as we saw, separating them lets you use the same test cases in multiple tests. So now, are we done with binary search? It turns out no, there is still one bug left, which takes us to tip number 6, look for special cases. So even if we've done an exhaustive test of all the small cases, there may still be bugs lurking. So here's the code again. There it is. There's one bug left. Does anyone see it who doesn't already know what it is? No one is going to see it. It's a very special case. Knuth wrote once that the first correct binary search was published in 1964, but this bug was found in 2006. The bug is that if the number of elements in the slice is very close to the maximum value for an int, then I plus j over 2 is the wrong way to do the calculation of the middle, because I plus j will overflow. And this was discovered back in 2006 in C programs that use 64-bit memories but only 32-bit ints. And that's not going to happen in Go. We made sure that that just wasn't a possibility. But since we know about the bug, and we don't know how someone else will adapt your code later, it's still worth fixing the bug. So There are two standard fixes to keep the math from overflowing. A slightly faster one is to do an unsigned divide. And so suppose we fix that. Now are we done? No, we're not done because, whoops, we went too far. We didn't write a test. If you don't add a test, you don't actually fix the bug. And this is true in two different ways. The first way is the programming way. We've all had it happen where someone tells us about a bug, we immediately know what's wrong, we go fix it, we send it back to them and say, it's still not working for me. And so at least if you write a test while you're doing that, and that happens, you can say, well, I'm sorry I didn't fix your bug, at least I fixed a bug. And the second way that this is true is the software engineering way, the time and other programmers way. If you fix the bug today, bugs tend to be mistakes that are very likely. And so it's likely if you did it once, you're going to do it again, or someone else will reintroduce it later. And if there's not a test, the bug comes back. It turns out this test is very hard to write because we need a very, very large number of elements, and we don't have enough memory for that usually. So okay. The trick here, there's usually a clever way to write a test that is some sort of hard case. And the clever way in this case is to make a slice of empty structs because they don't take up any space at all, so we can have as many as we want. And then to pass in a fake comparison function that always says, no, that element is too small. And that causes the binary search to walk all the way down to the end of the slice where the overflow is going to happen. And so if we revert our fix and we run this test, then sure enough, it does in fact fail. And then if we put the fix back, it passes. So now we're done. Now the bug is actually fixed. So tip number 8, not everything fits in a table. But lots of things do fit in a table. So here's one of my favorite test tables. This is from the fump.printf tests. Each row is a printf format and a value and the expected output. And the real table is far too large to fit on a slide, but here are a few lines from it to give you a taste. If you read through the table, you start to see what are clearly bug fixes. Remember tip number 7, if you didn't add a test, you didn't fix the bug. The table made each of these tests trivial to add, and adding them makes sure that these bugs never come back. So tables are one way to separate test cases from test logic and to make it easy to add new test cases. But sometimes you have to add so many tests that it makes sense to avoid writing Go syntax at all. And so here's a test file from package strconv for testing conversion between textual representation and floating point numbers. And you might think that it's too hard to write a parser for this kind of input, but once you know how, it's not that much work. And being able to define testing mini-languages is incredibly useful. And so I'm going to walk through the code pretty quickly just to show you that there's not that much to it. So here's the code. We start off by reading the file. Then we split into lines. And we have to increment line number because the slice index is 0, but that's line number 1. And then we cut off any comments at the end of the line, and if the line is blank, we skip it. And this is all pretty standard boilerplate, except we jump too far. There we go. And now we get to the good part, which is we split the line into fields, and we pull out the 4 fields that we expect on each line. By the end of the talk, I will have figured this out. And then we do the conversion based on whether we want float 32 or float 64 math. And finally, if the result is not what we want, then we print the error. And this is a lot like a table-driven test. It's just that we're parsing the file instead of ranging over a table. It doesn't fit on a slide, but it does fit on a single screen. So tip number 9 is that test cases can be in test data files. They don't have to be in your source code. As another example, the Go regular expression package includes some test data files that are copied from the AT&T POSIX regular expression library. And I won't go into the details, but I'm grateful that they chose a file-based testing strategy because it meant that I could copy their test files and reuse them for my implementation. And it's another ad hoc format, but it's easily parsed and easily edited. So tip number 10 is to compare against other implementations. Comparing against the AT&T regex test cases made sure that Go's package handled these various corner cases that someone else had already figured out were subtle cases that had to be right, and handled them the same way. And we also compared Go's regex package against the C++ RE2 library. And rather than linking against C++ code, we changed the C++ test to log every single test that they did to a file, and then we just read that file to check against those answers. Another way to store test cases in files is to have pairs of files, one for input and one for output. And so to implement Go test minus JSON, there's a little program called test to JSON that reads test output and produces JSON output. And the test data is pairs of files, test output, which is the input, and then JSON output. So here is the shortest file. The test output is at the top. That's the input to test to JSON. And it should produce the JSON output at the bottom. And then here is the implementation to show you some of the idioms for reading test data from a file. So we start by using filepath.glob to find all the test data. If that fails or it doesn't find any, then we complain. We fail the test. And otherwise we loop over the files, and then for each one we create a subtest named by just the base name of the file. And when we run a subtest with that name. And so if your tests are complex enough that it makes sense to have one in every file, it almost always also makes sense to use t.run, so that if one of your tests is failing, you can run just that test with go test minus run. For the actual test case, we have to read the file, and then we have to run the converter, which was highlighted in the split second, and then we have to check whether the results match. And so for the check, I actually started out just using bytes.equal, but over time it became worthwhile to write this custom function you can see called at the bottom called diffJSON that parses two JSON results and prints a nice explanation of what's actually different. Tip number 11 is to make test failures readable. There we go. Rewinding a bit, we've already seen some readable test failures with binary search. There we go. I think we all agree the pink box is not a good test failure, but there are two details in the yellow box that make these failures especially good. The first is that we check both return values in a single if statement, and then when there's a failure, we print the full inputs and the full outputs. And the second is that we don't stop after the first failure. We call t.error instead of t.fatal. And combined, these choices let us see the full details of each failure and multiple failures so that we can look for patterns. Like before, we saw that actually in both of these failures, the indexes are correct, but the Booleans are wrong. So moving back to test to JSON, here's how its test fails. This is what it looks like when it fails. Sometimes. There we go. It calculates which events are different, and it marks them very clearly. And so one important point is that you don't need to write this kind of sophisticated code to do these comparisons when you first write the test. Bytes.equal was fine to get going. But as the failures become more subtle and you find yourself in the test a lot more, that's when it makes sense to invest more time in writing clearer failures. Another issue with these kind of tests is that if the answers change, it can be really annoying to update the files. And so that's tip number 12, which is that if the answers can change, write code to update them. And the usual way to do this is to add a -update flag to the test. There we go. Here's the updating code for test to JSON. There's a new flag -update, and when the flag is true, the test writes the computed answer back to the file instead of calling diffJSON. So now if we make an intentional change, we run go test -update. That causes it to write the new answers out to the files, and then we can even git diff them before we check them in to make sure they look like what we expect. Staying on the topic of test files, it's a little bit annoying to have these pairs of files, to have two files. And so if I was writing this test today, I actually wouldn't do that. I would use something different, which is our next tip, which is to use textar for multi-file test cases. Oh boy, way too far. Come on, one more. All right, there we go. textar is a new archive format we designed a few years ago specifically to solve the multi-file test case problem. And the Go parser is in golang.org xtools textar. And I've also found parsers written in Ruby, Rust, and Swift. So we'll go to the next slide. Textar's design had 3 goals. First, we want it to be trivial enough to create, edit, and read by hand. Second, we want to be able to store trees of text files because we needed that for the Go command. And third, we really wanted them to diff nicely so they're easy to read and review. And there are some non-goals which mainly boil down to don't be a completely general archive format because that introduces all sorts of complexity that contradicts the first goals. So these goals and non-goals led to a very simple format. So here's an example. The textar file starts with a comment. In this case, here are some greetings. And then in general, there's 0 or more files that follow the comment, which are each introduced by a line with 2 dashes and a space and a file name and then a space and 2 dashes. And so this archive has 2 files, each of which are 1 line, named hello and g'day. And that's it. That's the entire format. There's no escaping, no quoting, no support for binary data. It's a sort of format that you can just write by hand. So here's a real use case in test data for a package that computes diffs. And the comment here is useful for people. It says what's being tested and where it came from. And then in this test, each of the archives contains 3 files. The two different files of any name followed by a file named diff. And so using the textar files is almost as trivial as writing them. So here's the test for the diff package we were looking at. This is the same sort of file-based loop, but we call parsefile textar.parsefile on the file. And then we insist the archive has 3 files, and the last one has to be named diff. And then we diff the 2 input files. Oops, went a little too far. There's a slide in the middle there. There we go. Then we diff the 2 input files, and we check that the result matches the expected diff. And that's the whole test. So you may have noticed the file data is passed to this function called clean before it gets used. And clean lets us add some diff-specific extensions for this test without complicating the textar format. And so the first extension handles lines ending in spaces, which happen in diffs. So lots of editors want to remove those trailing spaces. So the test lets us put a $sign at the end of the line just so the editors won't strip the space before it. And then we take the $sign out during the test. So in the example, the 2 lines at the bottom, they need to end in a single space. But in the test data, we put the $sign in so the editors will leave them alone. All right. And then textar also insists that every line in a file ends in a new line. But we want to test what diff does on files that don't end in a new line, because that's part of its spec. So in the test, we allow a literal $D at the end. And then clean removes the $D to produce a file that doesn't end in a new line. So in this case, the file called new does not end in a new line. Diff correctly reports that. So even though textar doesn't have all these complications, you can always layer your own adjustments on top. And of course, it's important to document those so the person who comes in next and has to work on these test cases knows what this means. But in general, annotating existing formats to create testing mini languages is a really powerful idea. So here's another example of an existing format that we annotated. This is a test for the Go type checker. It's a plain Go input file, but you can see we've added /error comments. And these comments are placed exactly where the errors should be reported. And so the test runs the type checker, and then it checks that it produces an error message with that message at exactly that location. And it also checks that it doesn't produce any other errors at other locations that we didn't mark. Here's another example from the type checker. Oh, I went too far before. Here's another example from the type checker. In this case, we have an assert annotation on top of the usual Go syntax, and that lets us write tests of constant arithmetic. So the type checker is already computing the Boolean values of all of these constant expressions. The only thing the test has to do is look for the calls to assert and then check that the Boolean there is a constant true. Here is another example of an annotated format. Ivy is an interactive calculator. You type programs, usually simple expressions, and it prints back answers. And the test cases are files that look like this. The unindented lines are the Ivy input, and the indented lines are the expected output from Ivy at that point in the transcript. And it doesn't get much easier to write a new test case than files like this. These annotated formats are extending existing parsers and printers. And sometimes it helps to write your own parsers and printers from scratch instead. After all, most tests involve creating or inspecting data. And those tests are always far nicer to work with if you're working with the data in a convenient form. We jumped ahead, that's great. These parsers don't have to be for standalone scripts and test data files. It's also possible to use them in regular Go code. So here's a fragment of the test for the code that runs deps.dev. This test sets up some database table rows. It calls a function that uses the database and that's being tested, and then it checks that the database contains the expected results. The insert and want calls are using a mini language for database contents that's written specifically for these tests. And the parser is as easy as it looks. You split by lines, you split each line into columns, and that's it. The first line is the column names. And the exact spacing in these strings doesn't matter, but of course it's nice that they're all aligned on the slide and you kind of want to keep them that way. And so to support this test, the team that wrote deps.dev also wrote a code formatter just for these tests. There we go. It uses the Go standard library to parse the test source files, and then it walks over the Go syntax tree to find the calls to insert and want. It pulls out the string arguments, parses them into tables, and then it reprints the tables back into strings, reinserts the strings back into the syntax trees, and rewrites the syntax trees back into Go source files. So this is really just an extended version of GopherConAU, and it's using the same packages that GopherConAU uses. And I won't show it to you, but it's not that much code. Now, this parser and printer took some time to write. Here we go. But now every time someone writes a test, that test is that much easier to write. And every time it fails or needs updating, it's that much easier to debug. And so if you're doing software engineering, then the benefits of spending time on this sort of thing scale with the number of programmers and the lifetime of the project. And so for deps.dev, already the time spent on this parser and printer has been saved many times over. And perhaps even more importantly, because the tests are easier to write, you're likely to write more of them, which results in higher quality code. So tip number 16, code quality is limited by test quality. If you can't write high quality tests, you won't write enough tests and you won't end up with high quality code. Now I want to show you some of the highest quality tests I've ever worked on, which are the tests for the Go command. And these bring together many of the ideas we've seen so far. So here's a simple but real Go command test. This is a text-R input with a single file, hello.go. The archive comment is a script written in a simple line-at-a-time command language. And in the script, env sets an environment variable to turn off Go modules. A hash sign introduces a comment. Go runs the Go command, which should run the hello world program, and that program prints hello world to standard error. So the next line checks that standard error matches the regular expression hello world. And so overall, this test runs go run hello.go, and then checks that it printed hello world to standard error. Here's another real test. Notice at the bottom that a.go is importing an empty string, which is not valid. And so the bang at the start of the first line is a not operator. It says not go list a.go. It should fail. And the next line, not stood out dot, says that there shouldn't be any matches for the regular expression dot on standard output, meaning there shouldn't be any standard output. And the next line says that in standard error, we should see an invalid import path error. And then the final line says there should not be a panic. All right, so tip number 17, scripts make good test cases. These scripts make it incredibly easy to add a new test case. Here is our smallest test, 2 lines. And this is a real test. I added it recently after I broke the error message that gets printed for an unknown command. And in all, we have over 700 of these scripts, from 2 lines up to over 500 lines. And these test scripts replaced a much more traditional test scaffold with methods. And this slide shows one of the real tests it replaced from the commit that introduced them. And the real test is behind the script translation. And the details don't matter except to notice the script is much easier to read and to write and to understand. So tip number 18 is try rsc.io script for your own script-based test cases. I just published this package on Monday, So ironically, it doesn't have enough tests itself, but it's this script engine that we wrote for the Go command extracted into a package so that other people can try it. And Brian Mills took the time to give it a very nice API, and we just hadn't posted it yet. And so we might put it somewhere more official later if it turns out to be useful. So if you do try it, let me know how your experience is. And the motivation for extracting the script engine was to reuse it in a different part of the Go command tests. And so this script is preparing a Git repository containing a module that we want to import during a regular Go command script test. And you can see it sets some environment variables, it runs a git init, it sets the time, it runs some more git commands to add a file to the repo, and then it checks that we got exactly what we wanted, including the right hash. And once again, our test did not start out this sophisticated or this complicated to implement, which leads me to the next tip. Improve your tests over time. There we go. Originally, we didn't even have these repo scripts. We created test repos by hand, and we posted them on GitHub or Bitbucket or wherever else had the right version control software. And that worked OK, but it meant that if any of these servers went down, our tests didn't work. And so eventually, we took the time to build our own server that could serve all of these things, and we would make the repos by hand and zip them up and copy them over to the server. And that was better. There was only one server that could take down our tests, but it still wasn't great. And so this script-based version now builds and serves these repos entirely locally as part of the test. There's no network involved. And now the repo descriptions are in the repository next to the tests that they're using, or that are using them. And they make it very easy to review what's going on in the repos. And this was a little bit of extra infrastructure, but it's also testing a lot of code. So if you have a 10-line program, you should not be writing thousands of lines of test helpers. But if you have 100,000 lines of code, which is where the Go command is approximately, then a few thousand lines of code to help you write better tests is absolutely a good investment. So that brings us to tip number 20, which is to aim for continuous deployment. So there may be policy reasons that in your particular setting you can't use continuous deployment. But you should aim for it anyway, because as I mentioned at the start of the talk, any doubts you have about whether that would actually work are helpful little voices that are telling you where your testing is maybe not as good as it could be and where it needs improvement. And so even if you never actually enable continuous deployment, aiming for it can help keep you honest and improve the quality of your tests and improve the quality of your code. So I mentioned earlier that the Go website uses continuous deployment. And on each commit, we run these tests to decide, is the server good enough to publish? And at this point, you won't be surprised that we wrote a little testing script language for these tests. Here's what they look like. Each test begins with an HTTP request. Here we get the main go.dev page. And then after that, there are assertions about the response. And each assertion is of the form field operator value. And here the field is body, the operator is contains, and the value is literal text that the body has to contain. And this test is just checking that the page is rendering. So it checks for some distinctive text, and then it checks that we got an H2 heading. To make it easier to write these tests, there's no quoting at all, so we don't have to escape the quotes or anything like that. The value is just the rest of the line. So here's another test case. For historical reasons, /about needs to redirect, so we just check that it does. Here's another test case. There's nothing special here, but this page is actually being synthesized. Whoops, thank you. We'll get there. There we go. This is checking the case studies page renders because it's synthesized from a bunch of other pages, so there's various things that can go wrong. Now we want that one. So another field we can check is HTTP response code. We'll get there. There we go. And here's a bug fix. We were accidentally serving these files instead of serving 404s, so now we want to say these have to be 404s. The next part here is another field we can test is the header, right? This was a small change to add this header verb. And in this case, the header content type for the main blog needs to be HTML, but the header content type for its JSON feed had better be JSON. Here's another example. This one uses irregular expression matching. See if we can get that on the screen. There we go. The tilde operator, and it uses \s+, which means any number of spaces, to make sure the page has the right text, even if, because of templates or whatever reason, there's extra spaces involved. Now that got pretty old, so we switched to a new field named trim body, which is at the bottom here. And that's the body with all the runs of spaces replaced by a single space. And this example also shows that in this case, we made it so the value can be multiple indented lines to make multi-line matching easier. And this is the kind of thing you can do if you have your own sort of mini language here. You can really customize it and make the test really, really easy to write. So we also have some tests that can't be run locally. Get there. But are still worth... Thank you for the tips here. All right. They're still worth running in production before we migrate live traffic to the server. So here are two of them. They're actually identical except for the URLs. They're not terribly readable. This is not like my idea of the best possible test. But all I had to do was add the support for post queries and then get these running, and that's good enough. If we added more of these, I would probably take some time to invest into improving the way these look in the spirit of improving over time as needed. But these are fine, and they make sure that the playground is going to be working when we switch to the new website. And finally, as usual, it's easy to add bug fixes. So this comment says that in issue 51.989, there were some talks that weren't rendering at all. And so this test is checking that the page does render in any future deployment of the web page, or sorry, the web server. And so no matter what we do, issue 51.989 is not going to come back. There might be other bugs. There's guaranteed there's going to be other bugs. But this page is going to keep rendering at least that much. And so that's better than what we had before. And so that's all the examples I have time to show you. But I have one final thought for you. We'll get there. There we go. I'm sure you've had the experience of chasing down a bug, and you get to the point in the code where the bug is, and you look at it, and it's just totally wrong. And somehow, though, it's wrong in a way that doesn't matter most of the time, or it's canceled out by something else that's wrong, and you stare at it and you go, how did this code ever work? And if you recognize that you wrote the code, you might think, wow, I got really lucky. And if you know who wrote the code and it wasn't you, you might think, wow, they are a bad programmer. And they got really lucky. But most of the time, the answer is not actually luck. The answer to how did this code ever work is almost always because it had a test. Sure, the code was wrong, but the test checked that it worked well enough in the context where it needed to run. It was correct enough for the rest of the system to work, and that's what mattered. So maybe the person who wrote the code was a bad programmer, but they were a good software engineer because they wrote the test, and that's why the overall system that contains this wrong code is still working. So what I hope you take away from this talk is not the specific details of any test, although I do hope you'll keep an eye out for good uses of custom parsers and printers, because really anyone can learn how to write those, and using them effectively can be a real software engineering superpower. But ultimately, these were good tests for their packages, and good tests for your packages may look different, and that's fine. But no matter what you do, make it easy to write, to add new test cases. Make sure you have good, clear, high-quality tests. And remember that ultimately your code quality is limited by your test quality. So invest in improving your tests gradually over time. The longer you work on a project, the better your tests for that project should become. And aim for continuous development, even if you can't do it for real, at least as a thought experiment, to understand what's not tested well enough. And overall, put as much thought and care and effort into writing good test code as you do into writing good non-test code. It's totally worth it. Thanks very much, and enjoy GopherCon.